Hello, I'm Seema and welcome to part 10 of the chapter Electrochemistry. The topic of this video and the consecutive few videos is going to be the conductance of electrolytic solutions. But before we come to electrolysis in the electrolytic solution and how they conduct electricity, there are a few terms that we need to be familiar with. Do you know when we walk on the ground because of friction. The ground provides friction and that helps us to stop our step where it lays and we don't slip and fall. If there was less friction, we would have fallen, we would have slipped and slid across the room or across the floor. I would like you to imagine a similar force like friction when when electricity is being conducted through a substance. When electricity is conducted through a substance, there is a certain friction towards it, or there is a certain resistance towards the flow of that electricity. This resistance is known by the same name, that is electrical resistance. So the first term that we talk about is electrical resistance. It is represented by the term R, and the unit in which electrical resistance is measured is ohm, OHM, and it is represented by this Greek symbol. What is it called? Omega. And the unit, if you really see what is an ohm, it would be kg meter square upon Simon cube area square. And electrical resistance in your study of physics, you must be knowing, is you calculate or you find out the electrical resistance with the help of a Wheatstone bridge. And since I do not remember my physics as much, I would suggest if you would like to go into more details, go into your physics books and talk to your physics teacher. They'll be able to tell you more about this. Now, what is this resistance or electrical resistance proportional to? What does it depend on? It depends on the length of the substance through which electricity is passing. The greater the length, the more is the resistance. So the longer the substance is through which the electricity is passing, the more distance it has to cover, and that is why it has to cover more of, it has to bear more of resistance. So resistance is directly proportional to the length of the substance, and it is inversely proportional to the area of cross-section. So if you imagine there's a rod, a metallic rod that is thin, or a metallic wire that is thin, and a thick metallic rod of the same substance, of the same length, then the resistance of the one which has a thicker rod, the area of cross-section is greater. Therefore, although the length is the same, the denominator becomes greater and the resistance, it becomes less. So the thicker the substance is, the more the area of cross-section, the resistance is inversely proportional to it. So resistance is directly proportional to the length and inversely proportional to the area of cross-section of the substance through which the electricity is passing. If you remove this sign of proportionality, you need a constant. So we do that. Resistance becomes equal to, the proportionality constant is known as rho, and rho length over area of cross-section. L is the length, A is the area of cross-section, and rho is known as the resistivity or specific resistance of that particular, of any substance. Every substance has its own resistivity. Therefore, it is also known as specific resistance. It depends on the nature of the substance through which electricity is passing. So rho is resistivity. In chemistry, the International Union of Pure and Applied Chemistry, that is IUPAC, by convention has accepted that we would choose to call rho resistivity instead of specific resistance. Although they mean the same thing, yet we prefer to call it resistivity. So instead of using these two terms where you use them interchangeably, we fix ourselves to one, that is resistivity. So rho is resistivity. How do you define rho or resistivity? So rho resistivity, whose unit would be ohm meter, of a substance is its resistance when it is 1 meter long and it has an area of cross section that is 1 meter square. So it should be, the resistance should be of a block, let us say, of a metal or whatever the substance that you're using to conduct electricity. It should be 1 meter long and it should have an area of cross section of 1 meter square. That would be the resistivity of a substance. And therefore it is usually reported in 1 ohm meter would be equal to, it is also reported in ohm centimeters. So 1 ohm meter would be equal to 100 ohm centimeters, or we could say 1 ohm centimeter is equal to 0.01 ohm meter. This is just mathematically relating the two so that you could use dimensional analysis to convert the units. Helpful in your numerical problems. Now the opposite of resistance is conductance. Resistance is stopping, some force that stops the electricity from flowing. The opposite of that would be that substance or that force that allows the electricity to flow. So that is known as conductance. So conductance is the inverse of resistance. It would be the opposite, you would say. So conductance is the inverse of resistance and it is represented by the letter capital G, and the unit for it is mho. I find this very interesting. Although we are studying science, here the inverse of resistance would be 1 upon resistance, and therefore its unit should have been 1 upon ohm. But here we do not deal with it mathematically, we deal with it a little bit like an English student, a literature student. If this was ohm, OHM, let us call conductance to be mho, that is MHO, the opposite letters. Although it is the inverse of resistance, that is 1 upon resistance. So if this is ohm, the unit mathematically should be ohm inverse or 1 upon ohm. Now conductance, since it is the inverse of resistance, it would be conductance G would be equal to 1 upon R, and let us substitute the value of R in the denominator. R is rho L upon A. So this becomes, G becomes equal to A upon rho L. Now since we do not want to have a constant of proportionality which itself is an inverse, 1 upon rho is taken as a different constant of proportionality and it is known as kappa. And kappa is known as 1 upon rho, and it is also the constant of proportionality. So what would G, if we had to write as, what would G be proportional to? G would be directly proportional to the area of cross section and it would be inversely proportional to the length of the substance. And 1 upon rho, or the constant of proportionality, would be kappa, which would be equal to 1 upon rho, which is known as conductivity or specific conductance. And just as in the case of resistivity, the IUPAC chose to use the term resistivity here. For kappa also, the term conductivity is chosen over specific conductance. Although when you say specific conductance, it means the conductance of every substance is different and it depends on its nature and it is specific to that substance. That is why we call it specific conductance. But by convention, we'll be using the term conductivity for kappa. The unit for kappa is Siemens per centimeter or Siemens per meter. And 1 Siemens per centimeter is equal to 100 Siemens per meter. This again is used when you have to convert the units. Helpful in numerical problems again. Now the magnitude of the conductance. It depends on the nature of the substance. How much will a substance conduct, or the magnitude of its conductance or specific conductivity of that substance, it would be that depends on the nature of the substance. How does it depend on the nature of its substance? Some substances conduct electricity very easily, and some would have more of resistance and some would have more of conductance. Those substances which have more conductance would be better conductors, and those substances which have more resistance would be poorer conductors of electricity. So based on the conductivity of different substances have been classified into 4 different categories. Those categories are: the magnitude of conductance depends on the nature of the substance, and conductors, these can be classified into 4 categories, that is conductors, semiconductors, insulators and superconductors. If you just take matter as such, we are not yet talking about the electrolytic solution. We are only talking about substance like metal rods or whatever substance generally which acts as conductors. So on the basis of their conductance, we divide them into 4 categories, that is conductors, semiconductors, insulators and superconductors. Let us understand these a little better now. Conductors would be those substances which have very low resistance and high conductivity. And that is why they really conduct electricity very easily. And there is a table of the conductivities of different substances or specific conductivities which is there in your NCERT book. I will insert that table right now. I would suggest that you pause the video here, look at the table and see how much of a difference is there in the conductivity. In that table, electrolytic solutions have also been added. And you know already about electrolysis that if you had, let us say, pure water, that would not conduct electricity much. But if you add common salt to it, it starts conducting electricity very well. The reason for it is that in water itself, in neutral water, there aren't as many particles or ions to carry the current. But when you add an ionic substance to it, the ions, they separate and a separation of charges is created. And these charges can move, and these moving charges help in carrying the electric current. So they turn into conductors. So you will see those electrolytic substances which act as conductors, and in this table you can really, I would suggest you pause it. Just observe the conductivities of these different substances in the table. Alright, so now coming back to our discussion, we were talking of conductors. Metals, let us take their examples. Metals and their alloys are very good conductors of electricity. There are certain non-metals also. For example, you have carbon black, you have graphite and some organic polymers. You know, carbon black and graphite were known earlier to be good conductors. But in a more recent discovery, it was found that certain polymers, they also can conduct electricity very well. So these organic polymers like polyacetylene, you have polyaniline, you have polypyrrole and polythiophene. These act as good conductors of electricity. So they also come under the category of conductors. And all these conductors, they usually conduct electricity as a result of the movement of electrons. So the carriers of charges in these substances are electrons. And they are, so we say they are electronically conducting, which means the carriers of charges or electricity here are electrons. The second category on the basis of their conductivity are substances which are known as insulators. Insulators are those which have very low conductivity, so low that it is almost negligible. We would say that they do not conduct electricity. For example, you have ceramics, you have glass and ceramics, they act as insulators. You must have noticed that when you have those electrical fuse wires, they are, the sockets that you have are made up of ceramic. Because the ceramic is non-conducting, it is an insulator. So you do not get an electric shock when you pull it out, pull that plug out of it, because you're touching the ceramic and you're not touching the wires. So these are, and wherever you have wires, you would use an insulator to protect it from getting electric shock. Even plastic wires, you have an insulation over wires, metallic wires, which is of rubber or plastic, which does not conduct electricity. So such substances which do not conduct electricity are known as insulators. Now then comes a third category, which are semiconductors or semiconductors. The semiconductors, as the name suggests, their conductivity lies between conductors and insulators. It lies somewhere between. Neither are they insulators nor are they conductors. They don't conduct electricity readily. They do not absolutely not conduct electricity. They do somewhat conduct electricity. So we would say they are semiconductors. They are in between. Examples of these are silicon, doped silicon. You have gallium arsenide are some examples of semiconductors. And then the fourth category comes, which is of superconductors. Now superconductors, they have zero resistivity. There is no resistivity. Or you could say that they have infinite conductivity. Now this is a very ideal situation. It has been noticed that conductors like metals, when you start bringing down their temperature, do you know, in the case of metals, as you raise the temperature, the conductance of metals decreases. They cannot conduct as much of electricity. Why? Because as you raise the temperature, the molecules, they vibrate. And when they vibrate, the resistance, they cause more resistance. Imagine you are running in a field where balls are bouncing. And you're running, if the temperature is low, let us say the balls don't bounce as much, so you can run through fast. But if the temperature is higher, the balls are bouncing a lot. And when you run, there's a lot of resistance because one ball comes from here, one comes from here, one comes from there. So it is causing more and more of resistance to your motion. It is somewhat like that. Electricity is running, and when it is running, the disturbance or resistance due to the movement of particles would be more, and therefore as the temperature goes up, the resistance of a substance increases, and therefore, since conductivity is the inverse of resistance, its conductivity decreases. So what happens in superconductors, if on increasing the temperature, the conductivity decreases, let us do the opposite of it. Let us take a metal that conducts electricity and start decreasing its temperature. So initially, it was found that at temperatures which were as close to 0 to 15 Kelvin, almost inachievable temperature. 0 to 15 Kelvin would be really low, close to absolute zero, minus 273 degrees Celsius is 0 Kelvin. So around that temperature, the resistivity, it almost becomes zero, and conductivity is maximum. At that point, the metal would start acting as a superconductor. There is no resistance at all, and therefore it is as if you've added grease to the machine parts of a machine. And when there is so much of grease, all that happens is the machine parts, they slip and slide along with each other. There is no friction. It is somewhat like that. There are no balls jumping up because the temperature has been lowered so much that now there is no resistance, and the substance starts acting as a superconductor. But the problem there was that these superconductors required abnormally low temperatures, and the amount of conductivity that it would show in comparison to the amount of expenditure you would do to bring the temperature down so much would not balance out. So it was not economically feasible to have such superconductors unless the need was so much that you needed a superconductor. So they have zero resistivity or infinite conductivity. Metals and their alloys at very low temperatures used to still do act as superconductors. But later it was discovered that certain ceramics and some mixed oxides, they can start acting as superconductors instead of 0 to 15 Kelvin at temperatures about 150 degrees higher than this. That is at about 150 Kelvin, which is much higher in and which is achievable. They start acting as superconductors. So now these find practical use because this temperature is economically feasible. It is possible to achieve this temperature, and the process would be economically feasible if, of course, it is not that feasible yet, but if required, this can be used. Now, the conductance in these substances, in the case of conductors, as we talked of metals and we've not talked of the electrolytic solutions as yet, they have, the conductance in these takes place due to the presence of electrons. And it is these moving electrons, so we call this electronic conductance. But in the case of electrolytic solutions, the ions carry the electric charges, and these moving ions, they cause the movement of or the carriage of electric current. So in them we say the conductance is electrolytic or ionic conductance. It is not electronic conductance, it is electrolytic or ionic conductance. So in the next video I'm going to tell you a little bit about this, and with this I'll wind up today's video. If you found it helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos on chemistry. Thank you for watching, and bye-bye for now.